means there is a foggy situation around, that we do not know whether this signal is from T 1 or from T 2. So, such a signal is called, or such an echo is called second time around echo, because it has come after the transmission of second pulse. Similarly, if here some signal comes after transmission of 3 pulses, we get a signal, then it is called third time around echo, and so on. So, this is the confusion which is normally caused, and this has to be avoided somehow. So, it is avoided by using a method which is that these adjacent pulses are given the different shapes. Adjacent pulses are given different shapes, so that they can be distinguished. Suppose these two pulses have different, if they would have been having different shapes, then what will happen, whatever the echo signal is, will be able to tell that this echo signal is whether it is from T 1 or from T 2, because the shape of echo pulse, though the strength or amplitude of signal will be different, but shape will be retained, and that shape which is retained will tell you that whether it is from T 1 or from T 2. This is a block diagram showing the basic pulse radar. Here we have trigger source, modulator, microwave oscillator, duplexer and antenna. Same antenna is used for receiver section also. Here it is indicator, duplexer give it to the mixer, local oscillator, IF amplifier, detector and video amplifier. Now, what happens? This is transmitter section. This section is transmitter section. Whenever a signal has to be transmitted, trigger source will trigger the circuit on, signal will be modulated as we saw that pulses, and that modulated signal is given to the microwave oscillator from where a signal is generated, and duplexer connects the antenna to the transmitter section and a signal is transmitted. When signal is transmitted, a reference signal is fed to the indicator as a measure of time, so that it knows that signal is transmitted at this particular instant. Then what happens? Duplexer disconnects the transmitter section and connects the receiver section. After getting reflected from the object, the signal is received by the antenna and then it travels to the duplexer. From duplexer it goes to mixer. At the mixer we have the received signal and local oscillator, which gives an IF. It is given to the IF amplifier, from IF amplifier detector, video amplifier and indicator. In the indicator, we know the time difference between the transmitted signal and the received signal, and as a measure of time we can calculate the range of the target. This angle data from the antenna is also given to the indicator. Constituents of this is trigger source, pulse modulator, microwave oscillator, duplexer, no noise amplifier, mixer and local oscillator, IF amplifier, detector and video amplifier, indicator or display, direction indication from angle data. Limitations of simple CW radar. CW radar has got some limitations: lack of isolation between transmitter and receiver, receiver can be burned out, masking of wanted signal by transmitter noise, introduction of flicker noise due to homodyne, it is not pure heterodyne, lack of matched filter in the receiver, unable to identify whether the target is approaching or receding, simple CW can't find it out, increased clutter compared to pulse radar. Clutter is a form of noise. So, as compared to pulse radar, it is more there because signal is continuously being transmitted and received. Measurement of range is not possible by using CW radar, because signal is continuously being transmitted. We do not know, there is no difference between the adjacent pulses or any of the pulses, the signal is continuously same, and we do not know when the signal started and when it ended, and we do not know, we can't find the range of the object by using simple CW radar. So, for that purpose we needed a radar which is called MTI, and this is MTI and pulse Doppler radar. Using the principle of Doppler frequency shift in pulse radar, the relative velocity of target can be determined. This is the one of the greatest application of this radar, MTI, moving target indicator radar. Here we use both the principles. We use the principle of pulse radar, we use the principle of CW radar. A pulse radar that utilizes the Doppler frequency shift as a means of discriminating moving from the fixed target is called an MTI or a pulse Doppler radar. MTI is moving target indicator radar, means whether the target is moving or it is stationary, it can be detected by the radar. This MTI radar detects all the targets, whether they are moving or they are stationary. All the targets are detected by using MTI radar, and from those targets which target is stationary and which target is moving can also be differentiated. MTI is a necessity in high quality air surveillance radar that operate in the presence of clutter. Its design is more challenging than that of simple pulse radar or a simple CW radar. It is very obvious thing that MTI is a very high quality air surveillance radar, because it operates in the presence of all the targets. Clutter means there are other targets also. One target is desired target, other targets are, suppose there are so many targets, out of those targets some are stationary and some are moving. So, to differentiate between the stationary targets from the moving targets, we have to scan all those targets, all the targets are detected, and then a specific mechanism or principle is used to shunt out the stationary target and to point out that these are the moving targets. So, its design is little bit complex as compared to simple pulse radar or simple continuous wave radar. A continuous wave radar is converted to pulse radar by providing a power amplifier and a modulator to turn the amplifier on and off for generating the pulse. So, what MTI is? It is advanced version of CW. Here CW oscillator, it is CW oscillator, it is receiver and it is indicator. As I told you earlier, in CW radar we use two antennas as compared to single antenna. Here by adding a pulse modulator here and power amplifier here, CW radar can be converted into MTI radar. The difference between simple pulse radar and pulse Doppler radar is that in pulse Doppler radar, the reference signal at the receiver is derived from the transmitter, whereas in simple pulse radar, the reference signal at the receiver is from a local oscillator. This is one of the basic difference. Second, here the reference signal acts as a coherent reference needed to detect the Doppler frequency shift. The phase of transmitted signal is preserved in the reference signal. This is called coherent oscillator operation. Let the CW oscillator signal be A1 sin 2 pi f t, and then the reference signal is A2 sin 2 pi f t. The Doppler shift echo signal can be represented as, echo is the difference between these two signals, this f d is Doppler frequency shift. This is very important, whether the target is approaching or receding, depending upon that this plus or minus sign will be used. If it is approaching, it will be plus, if it is receding, it will be minus sign. So, difference of these two is the echo. The reference signal and target signal are heterodyned in a mixer, and output is the difference frequency component. This just works as a heterodyne receiver. The difference frequency is the Doppler frequency shift. The stationary targets V diff is a constant. The voltage mentioned above are shown in the figure. Here all the voltages are shown. This is A1 sin f t, this is reference signal A2 sin 2 pi f t, A3 and A4. These are the various frequencies or various signals if we go by the block diagram. Sample of a waveform, how the CW can be changed into a pulse radar. This was a continuous signal. By using that, we have made it a pulsed version. These are the RF echo pulse trains. Otherwise, had this reference not been there, it would have been continuous signal. Moving targets may be distinguished from the stationary targets by observing the video output of an A scope. The display is seen on the A scope. We will just discuss what the A scope is. Echoes from the fixed target remain constant throughout, but echoes from the moving targets vary in amplitude from sweep to sweep at a rate corresponding to the Doppler frequency shift. The superposition of the successive A scope sweeps is shown in figure. The moving targets produce with time a butterfly effect on A scope. It is not appropriate for display on the PPI, it can be shown on A scope only. This is the pattern. These are the various targets, but out of these targets you can see some, this is 1, 2nd, 3rd, 4th, 5th, these are different sweeps and it will go in the reverse pattern also. Now, we can see this signal is same, nothing has changed here, but this signal is not same. Similarly, this signal is also not same. Here the amplitude is changing continuously, you can see it is changing, pattern is changing, whereas this pattern is same, this pattern is same, this pattern is also same. So, it means if this pattern is changing, it means the target is not stationary. For this section, for this display, for this echo, the target is not at the same point, it is changing its position, that is why its phase is changing. Similarly, target here is also changing its position, that is why its shape is changing. So, if we superimpose all these 5 displays or these 5 characteristics on each other, then what will we find, that this will remain same as it is here, this will also remain same as it is here, but here we will see because this pattern is changing. So, if we superimpose all these echoes, then what we will see, this will be forming a butterfly pattern. Similarly, here is also the pattern is changing, and if we superimpose the signal, we will see here also a butterfly. So, these two butterflies suggest that target is moving and all the other reflections show that targets are stationary. Here you can't tell anything from this, you can't tell anything from this, but if we superimpose all the signals, we will be able to tell that these targets are stationary and these two targets are moving targets. So, this is the display of MTI, moving target indicator radar. Delay line canceller, one method commonly employed to extract Doppler information, a form of suitable to display the PPI scope is with a delay line canceller. MTI is uses a delay line canceller to detect out the moving target or to differentiate the moving target from the stationary target. Here we have a receiver delay line which delays the pulse, the signal by 1 pulse, and then it is subtractor, 2 adjacent pulses are subtracted from each other, and then we have full wave rectifier. The delay line canceller acts as a filter to eliminate the DC component of a fixed target and to pass the AC component of the moving target. Typical MTI radar with power amplifier. Here we have pulse modulator, power amplifier, duplexer, mixer, stable local oscillator also called STELO. Here is another mixer. This is coherent or oscillator, IF amplifier and phase detector. Output of this phase detector is given to delay line canceller. Here is the delay line canceller. Output of that phase rectifier is phase detector is given to this delay line canceller, and this delay line canceller, what does it do? It subtracts two adjacent pulses. The response of two adjacent pulses is subtracted from each other. It differs in way in which the reference signal is generated. The coherent reference is supplied by an oscillator called the coho or coherent oscillator, which stands for coherent oscillator. The coho is a stable oscillator whose frequency is the same as the intermediate frequency used in the receiver. The output of coherent oscillator F c is also mixed with the local oscillator frequency F 1. The local oscillator must also be stable oscillator and is called stable local oscillator. The RF echo signal is heterodyned with the stello signal to produce the IF signal, just as in the conventional super heterodyne receiver. The characteristic feature of coherent MTI radar is that the transmitted signal must be coherent with the reference signal in the receiver. This is accomplished by the coho signal. The function of the stello is to provide the necessary frequency translation from the IF to the transmitted frequency. Any stello phase shift is cancelled on reception. The reference signal from the coho and the IF echo signal are both fed into mixer called the phase detector. Its output is proportional to the phase difference between the two input signals. This is another MTI radar with power oscillator transmitter. And here we stop. Thank you.